probably help if you could hear me. Yes. I didn't really show much of the math. I just kind of said assume the property and went from there. But I can show you if you'd like.
Okay, we're looking at 7A on the homework, which David had a challenge with.
Yeah.
So let me give you permission to share your screen and go ahead and show me.
Share screen. That one. There we go. Yeah, 7A. The deltas convolve with each other. So yeah, I just said assume the shifting property, convolve them together. That becomes t minus 1 plus 1, which is delta of t.
Okay. So you didn't even go to the integral. You didn't find it necessary to go to the interval.
Mm-hmm.
Okay, so that's perfect. Yeah, that's perfect. Okay, thank you.
If you really want to see more, I have what you just did, if you really want to show it.
Okay.
Like.
Aiden, go ahead. Go ahead and show your solution to 7A.
Okay, just give me a second. Okay, so yeah, this is exactly what he did, but I didn't write the convolution thing first, but you take your first function, which is delta tau minus 1, and then you multiply it times your second one, and then you have, so that was t of, or that was yeah, that was t of 1, right? I'm forgetting what the original function was, but you have to.
No, it was del of t plus 1. So you did a t plus 1 minus tau. Every place there was a t, you stuck a t minus tau.
Yes. And so my logic for this was, okay, when tau doesn't equal 1, the expression is 0 because these two functions only exist at 1. But when tau equals 1, this first expression, I think, was infinity. And then this expression becomes, at tau equals 1, it becomes delta t. So, and this was the part I was kind of confused about. I had the integration of infinity times delta t, d tau, which I didn't write it here, but d tau. But I was pretty sure that this would just be delta t. And I guess I was right. I wasn't too sure about that, but I got lucky, kind of.
No, I don't think you got lucky at all. I think it's a consistent way of thinking. Thank you. Anybody get, let's see. I'll go ahead and share my screen again. And ask if you got the other ones. Did you get this one? Actually, this one was too easy. I shouldn't have done this. I should have got del of t over 2. I'll probably assign that next time. And the sign also turns out to be too easy. And I'm going to change that and reassign that next time. Because one has to take into account, as I think we mentioned in a previous lecture, you have to take into account the derivative of the function. So it does turn out that the derivative of this at t is equal to 1. Oh no, I guess, wait a minute. The derivative of this crosses at what point?
T equals 0.
T is equal to 0. And what's the derivative of this function at 0? It's minus 1, isn't it? So that turns out to be a derivative of 1. So you get a freebie if you don't take into account the derivatives. It's the same thing here. If you take the, let's see, it's not free. Cosine of pi t. Did anybody get this?
So when you're talking about the derivative, I'm not sure what you mean, because all I did was evaluated the inside function, like where it equals to 0, basically.
Yes, and there's a temptation to do that. And
yeah, that's all I did.
Yeah, that temptation is wrong. Let me show you, see if I can get my math a little bit better this time. Let me show you why that is. Do you remember that del of AT was equal to 1 over the magnitude of A times del of t. Do you recall that this was the scaling theorem? And by the way, again, I've given up a long time ago. My typewriter A is the same thing as my script A. They're both the same. Do you recall that scaling theorem? Now, if you look at this a little bit, if you look at this really closely, what they're asking you to do is to look at a function f of t and look at the function at. The function of at, of course, is a line which goes through the origin, correct? And notice the slope of that line manifests itself in the scaling out here. So you need to know the slope of that line. Therefore, if you have, say, a really funky function, say g of t, and you ask yourself, what is delta of g of t? Now, Aiden, you're totally right. The only place that there's a delta function is when this argument goes to 0, correct? But notice we have to take into account the scaling there, the derivative of the function. So we're going to take this portion and we're going to put it under a big magnifying glass. And if we put it under a big enough magnifying glass, what are we going to get? We're going to get a line, aren't we? Let me try that again. We're going to get a line that goes through the origin, correct? And what's the slope of that line? The slope of that line is dg dt evaluated at t is equal to 0, right? So we can even call this, if we want to do shorthand notation, of g prime at 0. So therefore, our delta of gt, if we put it under the magnifying glass, is the same thing as delta of g prime of 0, delta of g prime of 0 times times t. In other words, this is the slope of the line under the magnifying glass. So this takes on the role of A, doesn't it? That takes on the role of A. So the result is this is 1 over A, whoops, 1 over A times delta of t. Or if we want to get all the way through it, it's 1 over the magnitude of g prime at 0 times delta of t. So it's not just looking at the 0 crossing, it's looking at the slope of the 0 crossing. Now, what happens if you have a really funny signal which goes through 0 here, goes through 0 here, and goes through 0 here, something like this? Well, here you're going to have 3 delta functions. Every time it goes through a 0, you're going to have a delta function. And that delta function is going to, in each case, be determined by the slope of the line that goes through the t-axis. So here we're going to have 3 delta functions. So for the sine, we're going to have an infinite number of delta functions, right? Because the sine wiggles, it goes up and down, and it crosses the axis an infinite number of times. So what you literally get is a comb function. You're going to get a comb function. So that's the importance of doing the derivative there. Okay, so hopefully that makes sense.
Okay, so
Go ahead, David.
So my error when I wrote that is equal to the comb function was a factor of pi.
I haven't seen your solution yet, but yes, there might be a factor of pi because the derivative of the sine of pi t at the origin is pi cosine, right? So therefore, you evaluate the cosine at the origin and you're left with the slope of pi. So yes, you are going to have a pi in there. Very interesting stuff. I think it's very interesting stuff. Okay, are there any other questions about the homework? Were you able to get these pretty well once we got the clue?
I had a doubt there with the clue, even with the clue.
Oh, you don't like the clue, huh? Okay.
I like it, but then for C, we have T over A minus tau. So I was not sure if, so I did both actually in the homework. If then for the result, I had to count A as a dividend under the T or under the tau when I change the sign.
Well, here's the trick. It literally goes back to Calculus 101. And I don't mean to say that in a condescending way, but it does. Let me show you here. What do we have? X of T over A minus tau. Was that the result? Was that the problem? I think it was.
Yes.
Okay. So it turns out that d dt, how'd that go up there? Okay, d dt of x of t over a minus tau is equal to what? 1 over a times x prime of t over a minus tau, correct? And then dd tau, now this is what you were asked to do the Fourier transform of. dd tau of x of t over a minus tau was equal to minus x prime of t over a minus tau.
Okay.
Okay, so therefore therefore you can write this as what?
So that's where I had a question, Dr. Marks.
Yes.
Because I got to this point, and from my understanding, that term that you have written there is just the derivative of some function with those variables plugged in.
Yes.
Like afterwards. So what I did was I kind of just treated that function as like, I kind of said, okay, now it's negative x prime of z, where z equals those things inside, and I kind of just treated like x of z like its own function. I didn't really know what to do after that point.
Well, let me suggest what to do here.
Okay.
Again, this is knowledge of the tools, and let's hope I get it right and don't make a fool out of myself. Okay, I would call this y of t over a minus tau. And in fact, in the tables that I gave you, there's an entry for that. Let me see if I can find the tables here. Maybe I didn't even get to that yet. Yeah, in the tables, this is a few slides ahead. We actually have, nope, that's the wrong tables. That's the functional tables. We want the theorems, yeah, right here. Do you notice in the table I gave you, Where'd you go, table? In the tables, I gave you this Fourier transform. Right? And this is a relationship which I would expect you to be able to derive. It's not that difficult, but it's a combination, it's a concatenation of the shift theorem and the scaling theorem together. Yes, Adam.
That one is wrong, isn't it, in the table?
Oh, is this the one that you corrected me on?
I think Chris is the one who sent you the email, but I caught it as well, yeah.
Okay, so what should this be?
It should be A times X of AU. So it should be, the A should be in the numerator. Not the
Oh,
denominator.
absolutely, absolutely, yes.
Mm-hmm. That one and the one above it.
Yes, it should. Okay, both of these should be A times X of AU. But the exponentials are correct.
Yes. Mm-hmm.
Okay, this is good. I appreciate it. I'm finding out little typos in my book all the time, and this is another one. So
And
let me.
I think that one's in the errata.
Is that in the errata?
Yes.
Okay.
Yeah, we found it.
Yeah, we came across that in our math, and then we went and found the errata, and it was already in there.
Okay, that's good. That's good. I'll show you the errata in a second. But here's the point. We get to this point, and we can compute this Fourier transform as corrected. We go back down here. We're doing our wigglies. And all of a sudden, this lets us know what the Fourier transform of this is, correct? And then to get the derivative, you multiply by j2 pi u. That was the derivative theorem. So whatever the Fourier transform of this is, to get x sub prime, you simply multiply by j2 pi u. I think I got that backwards. You can go up here and you can compute this. I did get that backwards. You can compute this from the table, and then whatever that is from the table, well, once you correct it for the t's, once you get it from the table, you just multiply it by a j2 pi u, correct? And that will give you the right result.
So one thing I had different than that, since you do the shifting, you have a tau in your exponential, and it's not just minus j2 pi u a, it's minus j2 pi u a tau.
Yes.
So would the a also come down?
That's a good question. One of the things, here's a sanity check you can always do. E to the minus j 2 pi u, you say t over a. Well, let's see, would that work here? Okay, my point doesn't work here. What I was going to say is you can always check, and the exponent here always has to be unitless. So if you have anything which has a unit in it, then that's problematic. But it looks like A here is itself, if both t and tau have units of time, then A itself is dimensionless. So you can have an A in the numerator. So it's okay. So I don't know what you're saying, Adam. Are you saying that the correction is incorrect, or?
No, the correction is correct. I just have an extra a in my solution than you were mentioning there.
Oh, okay. Okay. By the way, if you like, you can always do this. You can go to my website, robertmarks.org, and there is a website called the Handbook of Fourieranalysis.com. Handbook of Fourieranalysis.com. And you can see that there's some things up here, including the errata. I think this is maybe where you guys found the errata. And where's the errata? Resources? Yeah, here's the errata. If you click on resources, you get the errata. So these are corrections to the book, which I am going to add on to. And if you click on this, you will get the errata. And I'm glad to see that that table correction was already in the errata. So this is good. Handbook of Fourieranalysis.com is where you go. So again, I still pay bounty for anybody that not generates, but discovers errors in my book. So I appreciate that all the time. Okay, with that, let's go on to let's go on to any other questions that we have.
Dr. Marks.
Yes.
So on Adam's question, should there or should there not be an A in the out front when you take the derivative with respect to tau?
Well,
I got an A in there as well. I solved it from the integral, and then pull the derivative out front.
well, here's the situation. Let's see if I can not sound like Joe Biden here. Where's my scribbles? Yeah, the question is what do you Fourier transform? You're asked to Fourier transform this, correct? You're asked to Fourier transform this, but this is what you get. Oh, that's not what you. That's not in the table. You have a very nice transformation here. Oh, let's see, 1 over A. Okay, so this is correct. So you can Fourier transform this, correct? And to get this to look like this, you simply equate the derivatives. And you can see that x prime in terms of the d tau is related to the derivative with respect to dt. And you can equate the two and then perform the operation that you can look up. Does that, I don't know if that sheds light on it. That's what I'm hearing you with the A. Now you asked whether the A should be out in front or in the exponent. Was that the question? What's that?
We were talking about there was an A that we got from, we had an A in the exponent, and we had an A out front as well. Like there was 2 A's. You have the magnitude A.
Oh yes, you will have an
A.
Yeah, you will have an A is when you equate this to this, right? Yeah, there will be an A out front.
I got 2 A's out front.
Mm-hmm. I have minus j2 pi u a squared times a x u, or a. Minus j2 pi u a squared times x of a u e to the minus j2 pi u a t.
That sounds unusual. I tell you what, let me go ahead and I will work this problem and post it on the solutions. I'll give you my solution, okay? Because the a squared doesn't sound right. It doesn't feel clean to me that there should be an a squared there. And I think this is really good, by the way, because you know what this does? This lets you, this is an illustration of mathematics. When you do derivatives and when you do analysis, such as Fourier analysis, sometimes things just don't feel right. And there's an axiom, and I think it was first proposed by Richard Feynman. He said, if you screw up on your assumption of your mathematics, the mathematics is going to talk back to you, and it's going to let you know that you're making a mistake, and you better go back and trust your instincts there and figure out what's wrong. My instincts say that the a squared doesn't sound right here. I don't think we should get an a squared there. So there is something incorrect. I would like to tell you that I work out all the homework problems that I assign to you, but I can't. So I'm going to have to go back and take a look. Okay. Okay, good. Any other questions then on the material? Now, if you notice, some of these are in the book. The shift theorem was something that I derived in class, and I just wanted you to be able to repeat it. And I think that the rest are relatively straightforward. What about
So
6? Yeah, go ahead.
I was actually going to mention 6. So I found some discussions online, and the people I was reading weren't agreeing. So if two Fourier transforms are equivalent, are the two functions equivalent?
They are at all points of continuity. Do
Okay.
you remember we said we had that funky thing with if we had a discontinuity, we got the midpoint? Engineers, as engineers, we don't care about that.
Mhm.
So for an engineering answer is yes, they are all the same.
Okay. That's
And-
what I thought, but people were disagreeing, so I wasn't sure.
Well, they're wrong, and here I'm right. And this is very interesting because you know what it says? It says that and this is weird because it doesn't make any sense that the derivative convolved with the function h is the same as the function convolved with the derivative of h, right?
Well, actually, it occurred to me while I was working that problem that this is convolving two functions, which brings in like calculus integral and flip and shift.
Yeah.
And so it seems reasonable to me that that would provide some ambiguity to which function was derived and which was shifted.
Yeah, well, it turns out that it's indisputable because the Fourier transform of both of these is exactly the same. And Fourier transforms are unique. The forward mapping and the backward mapping are unique at all points of continuity, okay? Here's another one that isn't as obvious. What happens if you take the sinc of t and you convolve it with the sinc of t? Can anybody do that one in their heads?
That's just a rectangle?
Well, no, I'm not talking about the Fourier transform. I'm talking about the actual convolution in time. But you're very close, Adam.
Just another sinc of t, isn't it?
It's a sinc of t.
Yeah.
I mean, isn't that weird? The answer is yes. I always thought that was very weird that you convolve a function with itself and you get the same thing back. But indeed, both of these, this has a Fourier transform. Of a rectangle times a rectangle. And of course, a rectangle times a rectangle is nothing more than a rectangle. So yeah, they're both exactly the same. So you get a lot of weird relationships that are exposed by the Fourier transform, this being one of them. What other function convolved with itself gives you the same exact function back?
So the delta function would, wouldn't it?
Yeah, delta function. Delta function convolved with itself as a Fourier transform of 1. And that, of course, is equal to a delta function. So that's a cute little relationship. Okay. Let's go back to the homework, see if there's any additional questions. Did that answer the questions, by the way, for that one? I forget what the question was. What was the question? Oh, yes, about the derivative of the, yes, question 6. So the answer is yes, because they both have the same Fourier transforms. That's the way that you would prove, I would prove the equality of these. And for those naysayers online, I would ask for a simple counterexample. And by the way, the counterexample has to be righteous. You know, you can't use weird stuff. Okay, with that then, let's return to the lecture then. If there's no other questions about that. And I like this. I like that we work out these problems as we're working along. Okay, I'm going to talk to you now about delta functions. Not delta functions, array functions. Array functions are related to delta functions, but here's the thing. The array function is a periodic function, and it's equal to the ratio of 2 signs, right? Now, it looks like the denominator, you're dividing by a sign, for peak's sakes. If you divide by a sign, when that sign goes to 0, you're going to get something infinite, unless it's close. Well, you're going to get something infinite, right? Unless it's canceled out by something in the numerator. What does this look like if t is about equal to 0? Do remember that the sine of a small angle, the sine of epsilon, is about equal to epsilon. Do you recall that from trigonometry? Okay, so as t is equal to 0, this thing is going to go to pi mt over m pi t. So what we're doing is we're substituting the argument for very small values. So I said t is about equal to 0, and so this is equal to 1. So now when the bottom, at least at the origin, goes to 0, the array function goes to 1, and you can see that indeed here. 1 has similar canceling it out at all of the other 0 crossings of the sign. The array function turns out to be very useful in a number of different areas, and possibly you haven't seen it before, at least defined this way. But the reason that it's important is that, let's see. The reason that it's important is that a sequence of delta functions, a finite sequence of delta functions, corresponds to an array function. So therefore, if you have delta functions which go from minus n to n, where n is a integer, and it's 0 thereafter, then the Fourier transform of this is the array function. Notice the array function is parameterized by m. So from this Fourier analysis, you can see that m is kind of an index for how long the array function is. If you're into phased arrays, phased array antennas, you can see that these delta functions might model a very crude phased array of 2n plus 1 antennas. And if you are into antenna theory and far fields and such things, you notice that the far field of an array is equal to the Fourier transform of the original aperture, if you will. In this case, the aperture is a number of delta functions. So if we had a number of delta functions corresponding to transmitting singular points, then the far field would be an array function. So that's the reason we like to use an array function. The other thing that you'll notice is that if n goes to infinity, what do we have? We have a Coulomb function, don't we? As n goes to infinity, we have a Coulomb function. So we would expect that the array function, as n went to infinity, that would be equal to the Coulomb function, right? And yes, if we set n is equal to 55 here, actually 2n plus 1 is 55. So what would that make n? 22? So you have 22, no, 26, right? 2n plus 1 is equal to 55. What's n?
Yeah, 24.5.
No, 2n plus 1.
27.
27.
Oh.
Okay, so we have 27. We have 27 on one side. We have 27 on the other side. So, and then let's see, that's 54, and then 1 at the origin. So that's a total of 55. The point is not simple arithmetic division. It's that as we set n as equal to a very, very large number, that this begins to approach the Coulomb function, doesn't it, in the frequency domain? This is the array function for very large values of n. And we see that indeed we do. And those of you that do phased arrays know that if you increase n, if you increase the size of your array, you really are able to increase your directivity. Your directivity is the width of that beam that you're pointing into space. And so this corroborates this because we get the Coulomb function. Now, of course, in array patterns, we only go this much. We don't go periodic. You can imagine this part over here replicated to the left, and this is what we actually get, because this is cut off because of evanescence, and it only goes from like what, minus pi over 2 to pi over 2. So it only covers, I believe, if I remember right, 180 degrees. And so this is the meat of the array function. So that's the array function. It has very, very interesting properties. And if one wants to steer this beam, if one wants to move it over and say have the delta function right here, what do? Well, by the modulation theorem, you multiply it by an e to the j2 pi, whatever the shift is, right? E to the j2 pi shift. And that's exactly the way that phased arrays are steered. You mess around with the phase delivered to each antenna in order to steer the beam. And you are able then to move this main beam around to the left and the right and steer it to different directions. So that's the array function. Very, very cool function. Now we come to the gamma function. The gamma function is named after Vasco da Gama. That's a joke, by the way. Do you know who Vasco da Gama was? Anybody know who Vasco da Gama was? Glauco, you should know.
I know the name, but I don't remember.
He was a Spanish explorer of the newfound world, Vasco da Gama. I don't know what he's famous for, but he had the last name of Gama, so I thought it would be fun to say it's named after Vasco da Gama. But he was not a mathematician; he was an explorer. The gamma function, I believe, was determined by Euler. Euler came along and said, let's look at the factorial function. Let's do it n, and we're going to plot n minus 1 factorial. And we all know what factorials are. Just to review, 7 factorial is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what a factorial is. So we wanted to plot n minus 1 factorial. Okay, so let's do this for n is equal to 1. For n is equal to 1, what is 0 factorial? Do you remember what that is?
I think it's 1.
1. For n is equal to 2, we're going to have n minus 1, 2 minus 1, 1 factorial, which of course is 1. Yeah, 0 factorial is a little weird, but we just do that because it works. We go over here to 3 factorial. So we have 2 points on this curve, right? We have this point, we have this point. Then we go over here to 3, and 2 factorial is 2. And then we have 4 factorial. 4 factorial is what? Or, sorry, 4 n minus 1, so it'll be 3 factorial. It'll be 6. So it'll be up here somewhere, right? So the interesting question is there a nice pretty curve that goes through all of these points in a nice smooth fashion? And yes, there is. If we replace this discrete variable n by a variable c, this is the function that goes through all of those factorial points. So it's a analytic continuation of the idea of a factorial. It makes it continuous. So now we can talk about things such as 1/2 factorial and 3/2 factorial. Although that doesn't make sense from our original definition, we can talk about at least in an abstract sense. Now, this is the gamma function, and this will suffice for what we're doing. This is for the real part of the argument greater than 0. Mathematicians have taken the gamma function. They have extended it to negative arguments. Yes, there's a minus 17.3 factorial. And in fact, they have extended it to complex arguments. So there's a gamma function of the square root of -1 that has a value. But we're not going to be interested in that. I just mentioned it in case you ever come across it in your life. We're only going to be interested in the positive values. And for the positive values, this expression works very nicely. So that's the gamma function. Now, the gamma function, if we sample it, as you see down here, is equal to n factorial. So gamma of n plus 1 is equal to n factorial. That means that we have slipped through all of these different points. The other thing is that if we multiply, just like the factorial, I might ask you to show this. If we multiply gamma, well, first of all, let me just do this. Isn't n factorial equal to n times n minus 1 factorial? Yeah, the answer is yes, obviously. Well, in a similar fashion, C of gamma of C is equal to the gamma function of C plus 1. So we have this recurrence relationship also. Now, in the book, I think I give you the place that it's used primarily with what we're doing is gamma of n, and we have the gamma of n down, but we can also get the gamma of n over 2. And all we need for the gamma of n over 2 is the gamma of 1/2. Because if we have the gamma of 1/2, we can figure out the gamma of 3/2, 4, 5/2, 7/2, etc. simply by applying this formula. Okay, so that's the gamma function. Why do we have the gamma function? Are we going to talk about the Fourier transform of the gamma function? No, I don't think we are. First of all, notice it's a really funky function. It's funky because it goes to infinity, and if we were to do anything with this, we would have a function which would be impossible to Fourier transform. It doesn't, what doesn't apply is something called the Dirichlet conditions. And those are conditions which are required for Fourier analysis. And we didn't go through these, but just take my word that this thing doesn't fit the Dirichlet conditions and is something that we cannot take the Fourier transform of. The reason we do the gamma function is to, first of all, here's the gamma function for 20 for arguments up to 5. So this is kind of what it looks like. And again, it goes through all the n factorials. So right here, it goes through 1, it goes through, at 2, it goes through 1 also. At 3, it goes through 2. At 4, it should go through 6. And 5 is 24. So it should go through 24 here. And so it's a nice continuous function that goes through all the factorials. Very interesting stuff. But we use the gamma function in the definition of the Bessel function. Now, you might have seen Bessel functions before. How many have seen Bessel functions before? Okay, one, and I got one of these handshakes. Okay, I'm going to tell you why now not to be afraid of Bessel functions. Do you consider yourself a good master of trigonometric functions? You do. Yet I know, and I suspect without touching your keyboard, that none of you can tell me what to 1 or 2 significant numbers, what the cosine of 15 or 14 degrees is. Could you tell me? No, you couldn't, right? So why do you consider yourself such a big proponent of trigonometry, such an expert in trigonometry? I'll tell you why. Number one, you know what they look like. You know the wiggles. You know that the cosine and sine are both kind of a jump up and down. Number 2, you know the properties. You know that if you shift a sine, you get a cosine. You know if you differentiate a sine, you get a cosine. If you differentiate a cosine, you get a minus sine, and all of these different things. So you know the properties. You know how to manipulate them. And number 3, you know where to go if you need the cosine of 14 degrees. You know where to go, right? You got a calculator that can tell you that. So that's why you're comfortable with trigonometry. There's a whole set of transcendental functions. These transcendental functions were much more popular a long time ago, but their purpose and analysis is still very valuable. They were typically analytic solutions to different wave functions with specific boundaries. The Bessel function is one such function. The Bessel function turns out to be secondary only to the sinusoid in the analysis of higher dimensional signals. And so we're going to look at the Bessel function, but we're only going to look at specific values of the Bessel function. There's a fourth thing that I forgot to mention. You know the definition of going back to the sines and cosines. You know the definition of the sines and cosines, don't you? What's the definition of a cosine?
The horizontal component of the position of a point on the edge of a circle defined by, specified by the angle from like I guess positive x direction.
Okay, so what David is saying is if you have a point going around in a circle, and you look at the real part of it goes back and forth like this. And if you trace that out as the circle is going around dynamically, if you trace that out in time, you get a cosine. Is that pretty accurate, David? Is that what
Yeah.
you're saying? Okay. Here's my definition. I think x prime, x double prime is equal to x. It's a solution to that differential equation. Or I could say that it's equal to the cosine is equal to the summation of n is equal to 0 to infinity of cosine of x to the 2n over 2n factorial. What's that? There's a name for that infinite expansion.
Taylor series?
Yeah, it's a Taylor series, right? Now, which one of these definitions is right?
All of them.
All of them are right. And that's the point that I wanted to make, is that when you define a higher transcendental function, there is no singular way to define the function. You can define it in a number of different ways. But once you define it, you should be able to generate all of the other definitions from it. So we will end, I will talk about this a little bit, and we will talk about a Bessel function. Now, these are not just regular Bessel functions. These are Bessel functions of the first kind. And yes, there are Bessel functions of the second kind. And then there are really weird Bessel functions that don't even have names. Well, they have names, but they're not the third kind or things. But this is a Bessel function of the first kind. This is the only time we're going to use that. And here's the way I'm going to define it by this integral. I'm going to define it by this integral. Now, why would I ever define it by this integral? It's equal to this integral. I don't know what that means. I do know that I have a gamma of nu plus a half here. So this is where the gamma function comes in. Nu is a parameter. As long as nu is greater than 1/2, then this is the definition. Here is the reason that I want to define it this way. Notice that this is equal to this coefficient here. I'm not going to rewrite the whole coefficient because I'd hurt myself. It's equal to this coefficient times the integral from of 1 minus u squared nu minus a half times the cosine of zu. Now, what kind of function is this? And the integral is from 0 to 1, correct? As a function of u, this is what we're integrating. We're just looking at functions of u. Is this an even or an odd function? You'll see some of the power here of even and oddness. As a function of u, that's an even function, isn't it? As a function of u. What about the cosine? That's also an even function of u. So this times this is also an even function of u. So therefore, I maintain I can integrate from minus 1/2 or minus 1 to 1 and then multiply this by a half.
So then take out the 2 in the numerator of the coefficient.
I could, but that's too much bookkeeping for me. I'm at the end of the lecture. I'm tired of bookkeeping. But you're right. Well, here's the other thing. This is, whoops. Let's try this. Whoops. Okay. So it's equal to this coefficient again, times 1/2 times the integral from minus 1 to 1 of 1 minus u squared raised to the nu minus 1/2 power. Now you notice again, this is even. And I'm going to do something, and I'm going to explain why I'm going to do it in a second. I'm going to replace this second one by e to the j zu. Can anybody tell me why I can replace the cosine by the e to the j zu?
The real part of e to the j zu is equal to cosine of zu.
Because when you multiply that even times the odd sign and you integrate it like that, it's going to go to 0 anyways.
You're exactly right. You're exactly right. This e to the j zu can be deconstructed via Euler into the cosine of zu plus j times the sine of u. This is odd. This is even. If we multiply this even by this odd, that's going to be odd, and that's going to be make no contribution to the overall integral. I can likewise write this as all of this stuff times 1/2. And now I'm going to do the integral from minus to infinity to infinity. And instead of integrating from -1 to 1, I'm going to put a rectangle in there. This rectangle is just going to chop off the integration. This rectangle goes from -1 to 1, and it chops off the integration. And then we get this as times 1 minus u squared to the new minus 1/2 times e to the j zu. Now, can anybody tell me why I went through all of this trouble to remanipulate the definition to what I have here on the bottom?
Kind of looks like a Fourier transform.
It does. You're exactly right. It looks like a Fourier transform. In fact, if I set z is equal to, what is it, 2 pi t? If I set z is equal to 2 pi t, I exactly have an inverse Fourier transform on the right. So what I've done is I've manipulated this definition, which you can find in most books on Bessel functions, and I've manipulated it into the shape of a Fourier transform. And now I have a Fourier transform. And this will be a Fourier. I'm not going to go through the details, but can you see if you put the z is equal to 2 pi t that we would have a Fourier transform there? So we can see that, so we can see now why I chose this definition. There's other definitions of the Bessel function that I could have used. I used this one because it was fortuitous to get us to the Fourier transform relationship. Okay, remember some of the things that we would like to know about the sine and cosine. We'd like to know where you can get the values. You can go on, shoot, I think even an Excel spreadsheet and get Bessel function results. It's not that big, it's everywhere, certainly on MATLAB. What does it look like? Well, this is what the Bessel functions look like. They're kind of wiggly, right? And the one that we're going to be interested in, there's two that we're going to be interested in primarily, is the nu is equal to 0 and the nu is equal to 1. Now the nu is equal to 0, notice what it looks like. It kind of looks like a sine x over x, doesn't it? So that's how I remember the J naught. I remember it's kind of like a sine x over x. It doesn't have the pretty properties that the sine x over x does. In fact, its zero crossings are no longer at integers. You have to look them up or to compute them. So their zero crossings are no longer at integers. But it's an even function. It goes on the other side just exactly like this. And that's what I remember about it. It looks like a sine x over x function. The J1, which we'll talk about, is kind of like a sinusoid. It's an odd function because if we were to continue it, it'd go down here. And this function goes and it follows, it's kind of like a sine wave, except it kind of damps out. And the J naught appears in numerous sort of places. The J1 also appears in a lot of different places, but not as a J1. We're all familiar with the sine x over x. In two-dimensional analysis, there is a j1x over x, not a sine x over x, but a j1x over x. And we have to come up with a very clever name for it. And so we call it the jink. Okay. The jink is, as you see here, the j1 2 pi t over 2t. So it's kind of like a sine x over x function, but it isn't a sine x over x function. It's a j1x over x function. And we'll go down here and I'll show you what it looks like because we're running a little short on time. This is the jink function. So just like the j naught, the jink kind of looks like a sine x over x, doesn't it? It doesn't have the nice zero crossings, but it has a very, very nice relationship. Now you'll notice that this is what the jink looks like if we use the integral that we used before. It's a 1 minus u squared. You can see we can manipulate this, right? We can make it from -1 to 1 and then put the e to the j2 pi here. So we can manipulate it. So it's kind of like the Fourier transform of 1 minus u squared. You know what that is? What's 1 minus u squared? What's it equal to at 1?
Zero.
What's it equal to at the origin?
1.
Yep. And at -1, since it's an even function. Guess what it is?
Oh,
It's a circle. It's half of a circle. So half of a circle has a Fourier transform of a jink function. And we'll talk about that more next time. Now, in the meantime, I've assigned some more homework for this lecture. This is lecture number 5. And please take a look at it as well as practice problems from the text. And we're going to have those due next Monday also. So please, in the next couple of days, take a look at them and see if you have any questions so we can address them on Thursday. I really like the discussion that we had today. And I'm frankly surprised that we could have such a transparent discussion. But I think it's because the class is so small and you guys are so smart. Okay. Any questions at all? Okie dokie. We'll see you. We'll see you in a couple of days then. Bye-bye.
Thank you. Bye-bye.
Be of good cheer.
Everyone.
bye.
Hey, Dr. Marks, quick question.
Okay, hold on. You got to call me back. 1 second.
Sure.
Let's meet again.